Welcome everyone, and today it's our pleasure to have Mahir Hadzic from University College London, and he is going to talk about instability theory or stability theory for relativistic stars and galaxies. So please, Mahir.
Thank you, Changchan. Thank you very much for this kind invitation. Okay, so the title of the talk is Instability or Stability Theory for Relativistic Stars and Galaxies. And first of all, as the title suggests, it's going to be a result about stability of some sort of steady states. And it's going to be linear stability, or rather linear instability results. And to make things even better, everything is going to be radial in this talk. And so stars and galaxies is just sort of fancy names for steady states of particular kinds of PDEs that I will introduce shortly. So let's start like this. So the one sort of thing about giving talks that involve general relativity is that they easily get out of control because of the amount of technicalities, and it's very easy to sort of fall into that trap. So I made a deliberate effort to spend a lot of time on the introduction, hopefully convincing you that the problems are interesting and maybe giving you a little bit of context where the problems come from, and even some ideas about the proofs before we actually get into anything a bit more technical. Having said that, I realized also that I was a little bit too ambitious in what I announced I should be able to do in this talk. So we'll start off with galaxies, and then hopefully time remaining, I will be able to tell you a little bit more about the stars bit. So, okay. A customary picture at the beginning. The idea is that stars and galaxies can be, at least radial stars and radial galaxies are reasonable approximation to some objects that we see observationally. And certainly in astrophysics, these are objects that are studied. In particular, if you open up any sort of classical astrophysics book and you ask the question, how does one describe a star? You are given with a certain choice. You either want to model it as a Newtonian star, where the gravity is modeled as through Newton's theory, or as a fully relativistic object. And in that case, you have to use Einstein field equations. And a similar observation goes for galaxies. I guess what you should be able to infer from this picture, can you all see my cursor moving around? Okay, what you should be able to sort of infer roughly from these pictures is that at least some of these objects are indeed approximately radial. So it's not far off to study stability of radial objects from the point of view of applications. Okay, so to kill all the suspense, a stationary star for the purpose of this talk will be a steady state of the Einstein-Euler system, and a stationary galaxy will be a steady state of the Einstein-Vlasov system. Okay. In each case, we are coupling the gravity described by Einstein equations with a matter field. In Euler in case of stars, so it's a fluid, and in case of galaxies, we are using the Vlasov equation. Why Vlasov? Because we imagine a galaxy to be a collection of little particles, and they attract each other gravitationally. So you think of it as sort of a gas with many particles. And finally, this is a very important remark, even if it looks sort of trivial. We are interested in isolated systems. So that in this language of general relativity is encoded in the boundary condition known as the asymptotic flatness condition. So it's a statement that sort of at spatial infinity, the space-time you're looking at looks like you're like a nice flat Minkowski type space-time. And as I already mentioned, everything in this talk will be about linear properties, even though proofs will entail some sort of nonlinear ideas, and everything will be done in the radial setting. So in my mind, there are sort of three ways to talk about these steady states and motivate the study of their dynamical stability. And this is not necessarily the chronological order in which one should be sort of doing this. Motivation one comes from purely Newtonian theory. So you forget about the relativistic effect and you ask sort of similar questions to the ones, similar questions that I mentioned, to the ones that I mentioned. Motivation number two would be coming purely from sort of, I guess you can call it physics or geometry if you wish, from relativistic astrophysics. And then motivation number three is something that I will probably not have time to talk about pretty much at all, but let me mention it has to do with something called the criticality phenomenon. Okay. So let's talk about galaxies. And I will spend some time talking about Newtonian description of galaxies and what that means. Just as a brief reminder, I mentioned how in the relativistic case, if you want to talk about stars, you couple Euler to Einstein. Well, in the Newtonian case, you couple Euler to the Poisson equation. And similarly, if you want to talk about gravitational, if you want to talk about galaxies, you talk about the Vlasov-Poisson system. I should emphasize here that when I say Vlasov-Poisson, I will always mean gravitational Vlasov-Poisson. So the particles are attracting as opposed to the other possibility that they are repelling, which would then model something very different, a plasma. And again, this idea that you're modeling an isolated system, so what we call asymptotic flatness here will simply mean that you assume that the gravitational potential at spatial infinity dies off to zero. Okay. So that's pretty clear. So for the next maybe 10 minutes, I want to talk just about Vlasov-Poisson system. It's perhaps the easiest way to think about it is through the is the following. So the basic unknown in this theory is a function f, which depends on, well, 7 variables. T stands for time, and then the remaining 6-dimensional bit of the phase space corresponds to the spatial and the velocity coordinate here. Okay, and then so this number density f has the following interpretation. If you are to sort of integrate in an infinitesimal piece of the phase space, this function, you would obtain the number of particles in that portion of the phase space. Okay, and f satisfies the so-called Vlasov equation, which is nothing but a transport equation for this number density f. It's sort of the continuity equation, if you wish, and it's written up here. So this first bit, dtf plus v dot spatial gradient of f, this is the so-called free transport operator, and then it's and then you have to take into account the presence of gravity through this force field gradient x psi dotted with gradient vf. And so this is the form of the equation. I'll comment a little bit more on that, but the presence of the gravitational field. Oh, do you see this when I highlight anything, something? You can see that? Okay. By the presence of this gravitational field, you have to explain how psi couples back to the unknown f, and this is done via the Poisson equation. So the Poisson equation states that the Laplacian of the gravitational potential is the density, rho, 4 pi times rho, and then how do you recover rho? Which is a purely macroscopic quantity. It only depends on time and the spatial coordinate. Well, you recover it from the number density by integrating with respect to this to the momentum or the velocity variable v. Okay, and galaxies, nothing but a gas of particles, in this case stars, which attract each other according to Newtonian laws, and any collision in this problem is neglected. And this is sort of a pure transport problem. Let me just see if I can draw. So, is there? Can somebody help me? How do I write in Zoom? Is there a little?
Actually, so how do you write on your pad is the same thing. If you can write on your pad, then it's reflected on the Zoom as you are sharing the screen. That's how I do it. So if you can manage to write on your pad, then we should be able to see what you write.
Yeah, I see.
So if you open this file in Notability, you know Notability?
No, I don't.
No? Oh, okay.
How about annotate?
Annotate, but where is that? That's what I'm
Like
looking for.
you move your cursor and then do you see the annotate like above top of your screen?
You have to open the file with preview, not with tech.
I
What
see.
is the app you
I
are
see.
using
That
to
is the
open your
problem.
file?
Thank you.
Yes.
Okay. Would you guys be amenable to me opening this file in Adobe?
Sure, sure.
Yeah. Okay, I'll stop sharing. Just give me a second. And then I apologize for this. It's just okay. So let me move on with the talk. So one thing that one can say about the Vlasov-Poisson system, what I meant to say or explain here is that this equation is not terribly surprising. The characteristics of this system would be x dot equals v, and v dot equals negative gradient of c. And these are just Newtonian equations of motion in a gravitational potential. But anyway, so the problem is globally well posed. Okay, so this goes back to Pfaffel-Moser, Lyons-Pertam around 1990. Moreover, there are infinitely many conserved quantities. So the conserved quantities are the Hamiltonian energy and a continuum, in fact, of conserved quantities called Casimir's. Basically, any function of f, if you integrate it, over the whole phase space, you will get something that is conserved. And one other thing one can say about this problem, and I am saying this because this will not be the case for its general relativistic version, it's an energy subcritical problem. So a way to rewrite the equation on the previous slide is to write it through this Poisson bracket here. So it's dTf plus the Poisson bracket of hf equals 0, where h is the local particle energy. So this would be the conserved quantity for this classical ODE, classical particle moving in a gravitational potential. This would be the local energy. Okay, so this is again sort of highlighting a certain particular structure that is particular to the Vlasov equation. Okay. Furthermore, if I ask you to find steady states to this problem, and this is a classical question, what you would do, you would drop the t dependence here, and you would just say, well, let's find all functions f that satisfy this relationship, Poisson bracket of h and f equals 0. So if you do that, you reduce it to this equation here. But you know that h is conserved along the characteristics. This was the statement about the preservation of the particle energy. So any function of h, if you just stick it in here, any function, let's say phi of h, is also going to solve this Poisson bracket equals 0 for f. So if f is of the form phi of h, you're solving this problem again. So this gives you an idea how to make an ansatz for the steady state for this problem. You look for a function f, which is of the form some function little phi of the particle energy. You know that it automatically satisfies the Vlasov equation. And for convenience, I will, instead of writing it in this form, little phi of capital H, I will sort of choose to write it in the following form, capital phi of 1 minus this function, this energy, particle energy H divided by some sort of cutoff energy H naught. The idea here is, and you will see this in a second, I want to find steady states such that when this particle energy exceeds a certain energy h naught, then F will be 0. So it's sort of, it's just a vacuum outside. I'm interested in finding confined, compactly supported steady states to this problem. Okay, so this quantity capital phi, I will refer to as the microscopic equation of state. It should sort of echo the equation of state that you're familiar with maybe from fluid dynamics. And now, as I said, you have a certain freedom. You can pretty much plug in any capital phi you want here, but you have to make sure that this solves the Poisson equation. And what you get here is, well, Laplace psi is 4 pi times rho, but rho is just the integral of the density F with respect to V. And you plug this in and you obtain a certain integral differential equation for psi. This is how you find steady states. You can ask the question, for what kinds of microscopic equations of state, capital phi, can I find a steady state? And here's the answer. Assuming a reasonable choice on this function, capital phi, and by reasonable here, I mean two classes of steady states that are completely classical in astrophysics literature. First class are called the polytropes, and these are the analogs of so-called Lane-Emden polytropes in classical fluid mechanics, and the so-called King's galaxy. You have some sort of exponential ansatz here. So for these two classes, for instance, here's the statement you can prove. And this is very old. For any value of the central density of this galaxy, so you compute the central density, you prescribe the central density, you call it kappa, there will exist a unique, compactly supported, finite mass steady state of the Vlasov-Poisson system with a prescribed equation of state capital phi. So I give you the profile capital phi, and then there is a one parameter family of solutions parameterized through the choice of this value kappa, which is the central density. And if I vary this capital phi, in fact, I can obtain a continuum of steady states. And I'm saying here that this is not unlike the 2D Euler, where you also have an abundance of steady states available to you. So here's a picture that should hopefully make this a little bit more clear. So prescribing the capital phi, we get this one parameter family and of steady states. And the difference is, while capital phi is fixed, you can vary the central density of the galaxy. So here I'm plotting only the macroscopic density, which is only a function of R. Everything is radial. But you can imagine that you can take kappa as big as you want. So you can generate steady state solutions that are compactly supported of finite mass with central density as big as you wish. And this sort of class of steady states has fascinated physicists for a long time. And so the breakthrough sort of from the physics point of view came in the 60s and then 70s at the level of linear stability theory. So here's roughly what one should call perhaps Antonov's stability picture or scenario. Here's the claim. If you fix an equation of state, capital phi, with this property that capital phi prime is bigger than 0, so this function capital phi is increasing, then no matter how high the central density of your steady state, the corresponding steady state is linearly stable. So this was really shown by these three authors here in the early 70s, and there have been other works by physicists. But let me give you some intuition. If you remember, if you sort of go back and see what it means for capital phi to be increasing, let's just go back a couple of slides. Here is the ansatz. If capital phi is increasing, because of this minus sign here, that means that the steady state, this function little phi as a function of h, is decreasing. So the linear stability criterion of Antonov is saying, well, if the number of highly energetic particles in my galaxy is going down as the energy goes up, then the galaxy should be linearly stable. This is a sort of, it makes some amount of sense. And this was indeed shown in the physics literature. But you can ask, is this does this stability statement translate to nonlinear theory? So in the mathematics literature, a lot of progress was made starting essentially with the 1990s. And these works are attributed to Guo, Rein, Lin, Sanchez, Soler, Lemou, Meatz, Raphael, and so on. And sort of the final nail in the coffin to this problem came through this work of Lemou, Meatz, and Raphael from 2012, where they show the following. This is again, removing all the technical assumptions in the theorem, but roughly speaking, the following statement. If you have a steady state whose profile, this capital phi function, is indeed monotone, plus some other technical assumptions, then for any kappa, any value of the central density, the resulting steady state is non-linearly orbitally stable. So this statement of stability is orbital, and what that means is you can start close in some topology, and you remain close in that topology to the steady state, but you do not know what the solution actually does exactly asymptotically. Okay, so that's the statement, and the emphasis here is it doesn't matter at all how centrally dense your star is. Once you prescribe an equation of state phi, which is monotone and satisfies all these linear stability assumptions, then in fact it's non-linearly stable for any member of that one parameter family of steady states, no matter how dense you are in the middle. So now I will do something which is not very pedagogical. I'm going to sort of state the main result without introducing the system of equations. So our main result is the following. This idea that all you need to know about stability is the monotonicity of the profile as a function of the particle energy, is that this is enough to conclude stability is just wrong. So here's the statement. The statement in a nutshell is that this Newtonian picture, or what I call Antonov's stability scenario, is wrong for the Einstein-Vlasov system. As I said, I didn't introduce Einstein-Vlasov system, but this is exactly what you imagine it to be. And don't worry, I will introduce it later. It's the coupling of Vlasov matter to the Einstein field equations. So the statement is more precise. If I can fix an equation of state phi, which satisfies the monotonicity condition of Antonov, phi prime is bigger than 0, and then you can show that there is a choice of central density, kappa star, sufficiently large, such that if your steady galaxy is centrally so dense that this value at the center is bigger than kappa star, then you're linearly unstable. Okay, so the instability is there. You can in fact show that this instability, this is part 2 of the theorem, is driven by an exponentially growing mode. So in the context of Euler theory of stars, this would not be a particularly surprising statement, but in the context of the Vlasov equation, it is very often highly non-trivial to prove, to find eigenvalues or eigenfunctions to these kinetic problems. And finally, this is the third bit. Again, this is not a precise statement. If I were to write a precise statement, it would take several pages. For any kappa bigger than 0, the phase space will split into a stable, unstable, and a centerpiece, which are invariant by the linear dynamics. And the growth is at most algebraic on this center space. Okay, so sort of the third bit goes under the name of exponential trichotomy, and it's the one that I will not have time to explain today, but I will say something about it. So let me just move on if there are no questions. I want to comment on this result. So this quantity kappa, I introduced it as the central density of the galaxy, is in one-to-one relation to the so-called central redshift of a galaxy. What that means is, what central redshift is, if you emit a photon that is centered at the center of the galaxy and you receive it at its boundary, you can observe or measure how much it shifts to the red. You can sort of see that. And that quantity can be viewed as some sort of measure of how relativistic this galaxy is. So what our theorem really says is that if the galaxy is highly relativistic in this particular sense, highly redshifted, then it is going to be unstable. Now I will make another statement, which could be thought of as slightly controversial. Linear instability will easily imply nonlinear instability. So what I'm saying here is that once you have the growing mode, it's not terribly hard to believe that it's nonlinearly unstable. Modulo one fact, the steady states that I talked about are not always smooth. In other words, they exhibit they are definitely continuous in the sense that you have some density distribution which then continuously touches the vacuum and extends this and can be extended all the way to infinity. However, the density may form kinks. The derivatives of the density may not be continuous at the vacuum boundary. So any theory that wants to address nonlinear instability questions sort of has to deal with a well-positioned theory that allows for such steady states to be part of it. Another important statement. If this central density is tiny, if it's very, very small, then you can show that the steady state is actually linearly stable. But there is a dramatic difference between linear stability and linear instability in this context. In the context of Einstein-Vlasov theory, this problem is energy supercritical. So the sort of the linear stability is not a particularly strong information if you want to extend this to some sort of nonlinear stability result. Okay, and an analogous result holds for steady starts, which are the steady state solutions of Einstein-Euler, which basically says that, roughly speaking, that for very high central redshifts, stationary radial stars are unstable. All of this is joint work with Zhiwu Lin and Gerhard Rein from a couple of years back. Okay, the exponential trichotomy is the promised bit that I will not really have time to talk about, but I explained what it is, and it really relies on a certain framework that was recently developed by Lin and Zhang, and in particular goes under this tag name of separable Hamiltonian systems, which these two systems that I talked about are examples of. Of course, in order to apply this theory, you need to verify some problem-specific properties, and that in itself is a lot of work. But what sort of is really nice about exponential trichotomy, it's almost like setting a stage for the development of the theory of invariant manifolds, which is sort of a distinctly nonlinear theory, and it can be used as a building block for interesting dynamics. So if you numerically, for instance, perturb these steady states that I mentioned, you will discover that at least physicists claim that there exists certain sort of center manifold-like structures that separate the dynamics in the vicinity of steady states into sort of two typical types of behavior, one that likes to lead the dynamics towards collapse, and another one that leads the dynamics towards dispersion. I'm talking about the unstable steady states. So in order to even sort of think of approaching these types of questions at the linear level, you need statements like the exponential trichotomy. But we will simply not have time to go into this today. Before I even say anything about math, let me move to motivation 2 for this problem. And this is, I think, actually chronologically the correct motivations. The the problem of the stability of these sort of highly redshifted, or if you wish, highly relativistic self-gravitating objects really was motivated by the discovery of quasars. So these are so-called quasi-stationary, highly redshifted objects. Astronomers observed these objects; they were highly redshifted, and so they wondered if they are actually, if what the origin of that redshift is. There are two possibilities: either they're stable and have high redshifts, or the origin of redshift is something else, like the cosmological expansion. And so this attracted the attention of people like Zeldovich and Novikov in the Soviet Union, and Wheeler and Thorne. In particular, Zeldovich formulated something that I call the Zeldovich conjecture, but it's a beautiful, simple statement, which has been to an extent verified numerically, and it's the following idea. So, if you fix one of these equations of state, capital Phi, I mentioned that you have a one-parameter family of solutions. So the idea of Zeldovich is to plot a quantity called the binding energy. So the binding energy is the difference of the total energy in the context of GR. We will call this is the ADM mass, which is a conserved quantity for the dynamics, and the total particle number, something like a total mass. You can think of it that way. So you plot this quantity called the binding energy, and if interpreted correctly, what Zeldovich says is that as you move from the region of small central density to the regions of high central density, there will be a single point, actually, single value of this central density or central redshift, where you transition from stable to unstable. And this is, if you wish, a version of a turning point principle. So it's a schematic picture. This is not an accurate picture. It's just a schematic presentation. It sort of has a physical interpretation. The system starts here with a very small value of central density. You're stable. As you increase the central density, the binding energy gets higher and higher. So the system is sort of struggling more and more to keep things together. And then eventually the hell breaks loose, and you get into the unstable regime. So to relate our result that I just presented to put it in relation to this Zeldovich conjecture, what we know is basically that in this blue region, when the density of the galaxy is tiny, we are linearly stable. So here, and when the density of the galaxies is large, we are linearly unstable. And in the full sort of resolution of the turning point principle of Zeldovich, which basically means proving that there exists a single transition to stability, that's an open problem, and it's not clear if it's even true. But at least there is some numerical suggestion by physicists and Andreasson and Rein much more recently that suggests that at least in some settings this is indeed correct. Okay, so let me sort of delve a little bit into the proof, or just give you some ideas. And this is the time where I actually introduced the Einstein-Vlasov system. So this is how most talks in general relativity start. What are the unknowns? The unknown is a certain space-time manifold, which is equipped with a Lorentzian metric. So the signature is minus plus plus plus. And particle density F is supported. Okay, this assumption here means that all particles are normalized to have mass 1. All the stars have mass 1, so what is the dimensionality of the phase space? A priori, it's 8-dimensional because this is because the function F is supported on the tangent bundle, but because of this condition that normalizes the mass, you can reduce the dimensionality of the phase space by 1, so you get a 7-dimensional phase space. this mass shell is invariant under the geodesic flow. And in this case, the analog of the Newtonian equations of motions are just the geodesic, is just the geodesic ODEs. Because everything is in spherical symmetry, I can make our life much easier. I will choose the so-called Schwarzschild coordinates, where the line element takes this form. So it's e to the 2 me dt squared plus e to the 2 lambda dr squared plus the usual bit r squared, and this is the parametrization of the S2. And these two assumptions here, saying that lambda and me converge to 0 as I approach asymptotic infinity, that is the asymptotic flatness, because in that case, when you set r equal to infinity, this metric simply reduces to the familiar Minkowski metric. Okay. But I will skip the full derivation and just tell you what the equations look like. So if I were to sort of draw that analogy to the Vlasov-Poisson system, the easiest way to think of these equations is the following. The function f, the phase space density, satisfies again a transport type equation, which is our Vlasov equation, dtf plus tf, where t is a certain transport operator. Now you might be tempted to ask me what this is because you don't want to feel cheated, and indeed I'll show you. This is what it looks like. Okay, there's not much to learn. I'm not showing you to memorize this picture. However, what you can notice is that it's indeed a first order operator that looks a little bit like the Poisson bracket. So there is a me and lambda are the metric terms, and then you have some combination of the first derivatives with respect to x and v. Okay. Now, in the context of Vlasov theory, of Vlasov-Poisson, if you remember, the Poisson equation was Laplace psi equals 4 pi rho. What replaces the field equation here are the equations for metric coefficients, lambda and me. So lambda and me satisfy these two equations that relate the metric to the density and the pressure. And what are density and the pressure? If you remember, in the context of Vlasov-Poisson, the density was just the integral of f with respect to the momentum. And here you have similar expression, they look just a little bit more complicated. Okay, so rho is some average of f with respect to v and a certain weight, and the same statement can be said about the pressure. So that is the structure of the problem in Schwarzschild coordinates. If you choose to write it in this description, I can comment on the choice of coordinates later, but I should just emphasize that this is the way, for instance, that people like Zeldovich and Thorne and these guys also formulated the problem. Now, the analog of the particle energy, kinetic plus potential energy, in this case is the following quantity. It's e to the me times square root of 1 plus v squared. So you can check that this is conserved along the geodesic flow. And you can then repeat the theory that we had in the Vlasov-Poisson context in order to find the steady states. So like in the Vlasov-Poisson case, you can prescribe an equation of state capital phi and ask the question, how do I, which is just a function of h, the particle energy, and you ask the question, can I find steady states? So this is again sort of a classical topic in the context of fluids. In the context of Vlasov theory, there's a little bit more work to do, but if you cleverly choose your unknown, this quantity y of r, which is a log of this cutoff energy minus the metric coefficient me. So okay, this is not particularly intuitive, but the point is that you can find a nice elliptic equation that is satisfied by y, and this is a very famous object. It's called the Tolman-Oppenheimer-Volkov steady state equation, just in the kinetic context, and you can solve it. So the most systematic treatment of this goes to back to Ramming, Rein, and Randall. But the point is that for any choice of this initial quantity y of naught, which in this case is the central redshift, there exists a unique smooth solution a star which galaxy which is whose spatial radius is finite, and it has a finite mass. Okay, perhaps this is not terribly relevant. Here's a formal definition of the redshift. Redshift z is actually defined in terms of this metric element me, and it takes this form. And the point is that we actually work with a quantity kappa, which is related to the central redshift in this one-to-one fashion. It's not exactly the same thing, but I just wanted, for the sake of precision, wanted to say exactly what it is. And now for any fixed equation of state capital phi, well, not quite any, but for a wide family of those, like the polytropes and the king galaxy that I mentioned earlier, you will get this one parameter family of steady states of the Einstein-Vlasov system. They will be compactly supported of finite mass. So here's what goes into the proof of linear instability. Well, first we have to linearize. This in itself is an interesting story. And then we will perform a certain scaling analysis for this problem as kappa, as the redshift goes all the way to infinity. So this bit will, this can be thought of as a singular limit problem for this sequence of solutions to these elliptic stationary problems. And then, okay, I will explain this. There's a certain operator sandwich theorem that allows us to say something about the spectrum. But let's sort of start with linearization. I will just sort of flesh out the structure. So you fix a steady state, as I mentioned, they exist. You try to linearize, and after some thinking, you have to sort of eyeball the right structure, but there's sort of two ways to think about the problem. There's the first order linearization, which is of the form dtf plus. So this b kappa here is an anti-self-adjoint operator of first order, and this quantity here L kappa is a bounded symmetric operator. Okay, so I was mentioning earlier this theory of separable Hamiltonian systems. So this fits. This is sort of a way to write it to kind of fit it in that framework. But more importantly, what is this b kappa? B kappa to the leading order, forget about this metric coefficient e to the minus lambda kappa, is the Poisson bracket that we encountered earlier. And this is a Poisson bracket in this 6-dimensional phase space. And there is a sort of a zeroth order correction. Of course, I can give you the explicit formula. It happens if I click here, but perhaps for the moment, let's avoid that. Equivalently, you can write this problem in the so-called second order formulation. There's a trick here that goes back to, well, essentially Antonov, but in the context of Euler, Einstein-Vlasov goes back to Kandrup and Thorne, which basically states that you can also reformulate this as a second order problem, dtt f minus. F minus is the odd part of f with respect to the momentum variable v, plus some operator L kappa acting on f minus. And this operator L kappa is of second order. If you remember, b kappa was to the leading order the Poisson bracket. So it's a first order operator. So this object here is a second order symmetric operator. Plus an operator c kappa that can be thought of as a non-local but zero order operator. Okay, so in this structure is very interesting. It plays an important role for us. But you can think of this as sort of a poor man's Klein-Gordon-like operator. So this is like the mass term, and this is like the second order term that you have. It is unfortunately not nearly as coercive, if you wish, as the Klein-Gordon operator. But I will talk about that in a second. One other thing that you kind of have to believe me, the natural weighted space there's a space here of functions f that you have to weight in a proper way in order to get all these symmetry or self-adjointness properties that I mentioned, is this space here. So don't worry too much about e to the lambda kappa. This quantity is bounded, but there's this weight here, 1 over the derivative of the equation of state phi kappa prime of h of k. So this quantity at the boundary of the galaxy, this quantity will vanish, in fact. So this weight actually carries some sort of non-trivial information. But anyway, there's a natural Hilbert space within which you have self-adjointness, and this is not terribly different from something you might have seen in the context of stability of, say, classical Newtonian stars. So me not knowing much about spectral theory, the first thing that I would like to do is to find any growing modus to minimize an expression of this type. So this is just like the Rayleigh-Ritz principle. So if you try to minimize this expression, this self-adjoint operator acting on f, inner product f in the right space, under the right constraint, the answer is that you will fail, and not only will you fail by a little, it will be a complete miserable fail. The best way to think of the reasons for that is that this operator that you're trying to, the operator that enters into this minimization problem is sort of leaks compactness in several directions. It's not coercive enough, and this has to do with the following. Even though I'm working in radial symmetry, a radial symmetry in the context of Vlasov theory means that you can apply a rotation, an SO3 transformation simultaneously to x and the v variable, and keep the problem invariant. That's the meaning. So the actual, after this radial reduction, dimensionality reduction, the actual phase space still remains three-dimensional. And this is the reason why it's hard to minimize. And this is not typical only for Einstein-Vlasov. It's actually an issue related to the Vlasov theory in general. So you have to do something slightly more sophisticated. And the first thing we did was to understand what happens when this central redshift kappa gets extremely large. Okay, so this is in a way a separate question. You should think of the central redshift getting extremely large as the opposite of the Newtonian limit of this sequence of elliptic problems. So it's something called the ultra relativistic limit. And you would like to understand what happens. So the first, perhaps not unnatural guess, if I give you a sequence of steady states whose densities, for a, say, moderately small choice of central density, you get this radius r kappa prime. And then if you make the density slightly bigger at the center, the steady state might look like this. So if you enlarge kappa, eventually, you might conjecture that this radius here is maybe going to 0 or something like that. And this is wrong as well. So, and it's in fact a theorem. Even if you send the central density, or the redshift is equivalent in this case, to infinity, these radii here will converge to some finite value, which I call R infinity. So if you, in other words, in this large kappa limit, it's really not clear how to extract some sort of non-trivial scaling limit. So this was a big insight for us. Let me just emphasize. In fact, you can say something much more precise, as this is the direction of increasing kappa. So you start here very Newtonian, and then you increase. And if you compute the mass and the radius for a typical steady state of this kind, they will sort of spiral into a finite point. They sort of spiral into a finite point, and your R infinity is somewhere here. So the answer to this issue is to zoom in onto the problem on the right scale. So e to the -2 kappa corresponds in physical variables to 1 over the central redshift squared. It's a sort of a physical parameter. So as kappa increases, what we did, we rescaled these variables, the density and the other variables, so that we zoom onto this picture in a window of size e to the -2 kappa. Okay. In other words, we are considering some new functions, let's say rho kappa tilde, defined as rho of e to the 2 kappa r. Okay. If you do that, so this is a dynamic window as you change kappa. As you change kappa, this window is shrinking. But if you do that, then you can, as kappa goes to infinity, you can see some non-trivial limit. And this is a nonlinear result. In that above window, roughly speaking, we can show that there is a universal attractor for this dynamics, for the density and the other steady state parameters. The macroscopic density, the metric field mu kappa, similarly for lambda kappa, we can actually exactly say what they converge to. And when I say this is a vague statement, what this really means is after appropriate rescaling, you discover these universal numbers. And these numbers actually have a meaning. They correspond to something known as the Bisnovaty-Kogan-Zeldovich solution, or also known as the BKZ solution of the massless Einstein-Vlasov system. The situation is the following. If you have this sequence of steady states and you rescale at the right scale around the center, and you send kappa to infinity, you will discover a steady state of the massless Einstein-Vlasov system. What this really means, this in itself is sort of interesting, but what this really means for us is that at least in some region around zero, when this galaxy is extremely dense, we can get very precise information on what the steady state actually looks like. So this is here. We have very precise knowledge of the coefficients of our otherwise highly non-explicit linear operator in this tiny window near the origin. Okay, and this is great because that means that if we can choose a test function for the second variation, we can choose a test function for that quadratic form that you saw, localized spatially to that particular window, where we know pretty much to high order of precision everything about the operator. And this, after some struggle, this is what allows us to actually find a function that makes the quadratic form negative if kappa is extremely big. And this is okay, so perhaps in a somewhat fancier language, this means that the negative Morse index of this operator L kappa, negative Morse index is just the maximum dimension of the space that makes the quadratic form negative. We can basically show that it's bigger or equal than 1, okay, for sufficiently large kappa. In other words, we have a way of finding a nice test function that makes the energy negative. So this is not yet equivalent to saying that we have an eigenvalue which is negative. So the third ingredient, and hopefully I will be in time to finish this. The third ingredient is something that we call the reduced operator. So the idea here is that, well, many things could in principle happen, even if you know that the Morse index of your operator is, let's say, bigger than 1. In other words, you have a test function that makes the quadratic form negative. Something crazy could happen. You could maybe degenerate. You could have infinite. Maybe the Morse index could be infinite. It's very easy to sort of not understand what's really going on. But there's this beautiful trick. So what we do, we next find a macroscopic operator. Macroscopic here means something that is like the usual Schrödinger operator that lives only where the unknowns only depend on R, on the spatial variable. And it takes this sort of suggestive form of minus Laplace kappa plus V kappa. So minus Laplace kappa is not a Laplacian, but it's almost like a Laplacian. It's the suitably weighted version of the Laplacian in 3D. And it's sort of, you don't have to draw much intuition, but it's sort of like the Laplacian decorated with the correct weights. And these weights are sort of harmless. They're bounded from below and above. And the negative potential, V kappa, which memorizes the presence of memorizes the steady state through this very non-local operation. You're integrating the steady state times the particle energy squared with respect to V. Okay, what one should say about this is that this potential V kappa is compactly supported in space. It's negative, and here's the announced sandwich lemma. This operator L kappa, which governs the linearization of Einstein-Vlasov, even though it lives on a 6-dimensional phase space, is in a certain sense sandwiched between these two copies of this Schrödinger type operator that I just introduced. What this means specifically is that for any psi in the domain of this operator S kappa, there's an F in the domain of this operator, so that one quadratic form dominates the other, and vice versa. This is, you sort of have to eyeball this operator S kappa, but once you've done that, then life is much nicer, because it allows you to, for instance, conclude, this is not the only way to do it, but for instance, you can conclude that the negative Morse index of the operator L kappa of Einstein-Vlasov linearization is finite. Why? Because it's bounded from below and above by the negative Morse index of S kappa, which being basically a minus Laplace plus a compactly supported potential, by classical theory has to have a finite negative Morse index. So there can only be finitely many bound states below zero. And okay, after this, you still have to do some work, but these are just some sort of general ideas that should tell you how we approach this problem. With these tools in place, we are able to also apply the theory developed by Lin and Zhang, and this, in the end, altogether yields the statements that I mentioned at the beginning. So I'm out of time, so I'm not going to say anything about the turning point principle for the stars. Thank you.
Thank you. So let's thank Mahir for the talk. And anybody has any questions, please just unmute yourself and speak out.
So I have a question. For the, I think that you mentioned for the Vlasov-Poisson, we have like a very good well-positionist theory if one wants to go to the nonlinear theory, right? For this Einstein-Vlasov, what is the status of the, say?
So for the local well-posedness, you can sort of apply kind of standard ideas by now of Choquet-Bruat, and you can prove local well-posedness in some Sobolev type spaces typically. That's certainly doable. Also, if you are close to vacuum, then it is known that Einstein-Vlasov system is stable. So small perturbation.
That's for the small data.
That would be the small data, exactly. That would be the small data result. And other than that, I'm not aware of any, other than the existence of, say, steady states, I'm not aware of any global in-time results for the nonlinear problem. Yeah. Yeah. Right. So the small data result was shown actually not too long ago. There are two proofs. Lindblad and Taylor have one, and then Smulevici and Zhiwu and Feynman. That's the other one. Yeah.
Thank you.
You're welcome.
Okay, so any other questions? So let's let's thank Mahir again, and
You're most
thanks for
welcome.
coming
Thank
to
you.
the talk.
Thank you. Yeah.